B, we want to show that the Bayes estimator can be written up in another way. And in particular, we actually want to show that the Bayes estimator can be written up in a way that has nothing to do with the distribution of theta. And that's kind of interesting in a sense because um, earlier when we wrote up MK, well, you see that we have something with f theta of y in here, right? But interestingly enough, we can actually write this up in a way where the Bayes estimator does not need to be expressed using anything that has to do with the distribution of theta. In this case, not in every case, but in exactly this case. Okay, so and this is in particular the case where we see that we only have one observation and it's Poisson distributed given theta and so on. So let's try to show this result. We have already established an expression for MK that we see here. So we can use it in the sense that we see that this expression also has 1 divided by the probability that x is equal to k. So it suffices to show that this expression without the divided by probability that x is equal to k is the same as k plus 1 multiplied by p of x equal to k plus 1. So it suffices to show for k equals 0, 1, 2, and so on, that the integral from 0 to infinity of f theta of y multiplied by e to the minus y multiplied by y to the k plus 1 divided by k factorial dy is equal to k plus 1 multiplied by the probability that x is equal to k plus 1. So let us take a look at how we can show that. Well, first of all, let us note that we want to, in some way, factor out a k plus 1. So we can multiply by k plus 1 on the outside and then divide by it on the inside, in which case we will then have y to the k plus 1 divided by k plus 1 factorial dy. Now that's pretty nice because now we have the k plus 1. And the only thing that we need to check now is to check that this thing here is actually the probability that x is equal to k plus 1. So let us try to see if this integral is equal to the probability that x is equal to k plus 1. The way we do that is look at the probability that x is equal to k plus 1. And let us note, using the double expectation property, that this is equal to the probability of x being equal to k plus 1 given theta, and then taking the expectation of that thing with respect to theta. And if we try to do that, then essentially what we find out is, well, let me just put in the density of theta since I am trying to find the integral of something where theta is the stochastic part. And then what we're going to do next is multiply by the probability that x is equal to k plus 1 given theta, right? So given theta equal to y dy. And what is the next thing that I can do here? Well, I know that given theta, x is Poisson distributed, and thus this point probability is equal to the point probability in the Poisson distribution with parameter y evaluated in the value k plus 1. Am I doing the right thing here? I think I'm doing the right thing here. Okay. And this is exactly what I asked up here. Is this equal to the probability that x is equal to k plus 1? Yes, it is. And so now we are finished. because now we have shown that maybe I should write this up just nicely for once. So I have shown that mk, well, that was equal to 1 over the probability that x is equal to k multiplied by the integral of f theta y e to the minus y to the k plus 1 divided by k plus 1 factorial dy, and then multiplied by k plus 1 out here. And I just established that this integral is equal to the probability that x is equal to k plus 1. So this is k plus 1 multiplied by the probability that x is equal to k plus 1 divided by the probability that x is equal to k. And hence the Bayes estimator of x given theta in this case does not at all depend on theta.